Just to refresh your mind about when we talk about carbon capture is basically talking about a delicate separation process in which we're interested to take out CO2 from a gas mixture. So for example, here I'm showing a point source, which is a flue gas that is coming out from a power plant. So the job for carbon capture box is basically to do the separation, send CO2 out from the matrix of the gas for compression or utilization, and then the rest to the environment, which are basically safe gases such as nitrogen and oxygen. And when we zoom in on carbon capture box itself, we see that this is basically a two-step process. The first step is the separation stage, and the second step is basically the concentration step. In the separation step, we have a sorbent that is selectively capturing or absorbing the CO2 gas. And then basically what happens here, this separation is done, then we send it to the concentration stage where we apply some sort of energy to be able to regenerate the sorbent, sending it back, and then concentrate what we capture in the first step. So basically doing the concentration step. So in terms of the energy point of view, the energy intensive part would be this step. So thermodynamically favorable here, but here we need to spend energy to be able to regenerate the sorbent and also doing the concentration. So conventionally, what has been done is using steam as the source of energy, as the driving force. And the most conventional process using an amine absorbent, such as MEA, and then applying heat or thermally driven process to regenerate that capture CO2 with amine. These processes are very mature. They has been implemented at high TRL. But if we want to be picky and then point out some of the issues, some of the challenges that these technologies are currently facing, we could point out to the high rate of absorption degradation. It requires replacement partially or completely the absorbent after some time of operation. They relatively have large footprint. It's not relatively easy to retrofit, especially for those point sources that we already built. And also they rely on high temperature operation and also relatively high CapEx and OpEx. What we're trying to do by revisiting the source of energy, bringing electricity to the picture. So as opposed to having a thermally driven process, we do an electricity driven process. So here the way we look at the system is very similar to electrolyzer or fuel cell. That is, the process is basically an electricity driven process. These processes are less mature compared to the conventional amine based technologies, and it requires still a lot of R&D, but there are some big hopes. For example, they are very modular and easy to scale up, basically adding more module. It gives us the ability to increase the scale of carbon capture in this case. It has a low to medium footprint, easy to maintain. If something is not working, we just replace and work on a specific module as opposed to the whole process. It's easy to retrofit. I always use the example of your cell phone battery. It retrofits easily into your pocket. So this would be pretty much the same analogy there. It's the room temperature process, plug and play, and low to medium CapEx and OpEx based on the current projection. So our invention was basically looking at the process. Can we leverage on this electricity-driven processes to have sort of an all-in-one process? So basically what we have here eventually is a container style capture unit. We call that small modular electrochemical container. So these are the 40-foot container, standard containers, which we have basically, if we look at the boundaries, CO2 rich coming from a flue gas in, and eventually purification and separating the CO2 from other gases. When we zoom in, these are similar to electrolyzer, basically a bunch of electrochemical stacks. And further zooming in, when we look at the electrochemical cell, we see that basically these are a typical electrochemical unit that is exposed to two gas phases. So here we do the separation on one side, and then we do the concentration on the other side, and using two gas diffusion electrodes. And by doing that, we're doing all in one kind of aperture. So capture, concentration, and separation, and leveraging on the engineered gas diffusion electrodes. But the key question is why this? Why does it matter? Like this invention? I think we can leverage on all the benefits that I mentioned, modularity, and also the plug and play nature of this. But it all comes to the economics of the process. So we try to look at how much does it cost to capture 1 ton of CO2, the levelized cost of capture using this specific technology, and take a more conservative approach because these are not at high TRL to be able to adapt a lot of practical inputs. Rather, we have to basically project. So we took sort of a conservative approach to do the projection. And then going from Gen 1 that we developed before with membranes to Gen 2, we were able to basically reduce the cost significantly, bringing it down to roughly $70 per ton CO2. And the major cost reduction was basically driven by the motivation of getting rid of the most expensive component, which was the ion selective membrane in Gen 1. And then by doing some typical R&D on the metrics that we are very comfortable with, such as the current density and efficiency, we have a projection of bringing down the cost to less than $50 per ton CO2. And to put this into perspective, this is basically the graph is showing some of the conventional processes that are out there that are implemented at different point source sectors, for example, a natural gas or coal power plant. And then we were able to compare the cost here. And as you see, especially Gen 2 is very competitive to what we have already in terms of the conventional point source carbon capture. So overall, why does it matter? We think that this is a very cost-effective solution for point source decarbonization. We're still working on DAC, whether this is also cost-effective for DAC, but that's a different question. A little bit on something that we so far we achieved. Just a proof of concept is already published. We highlighted the simplification of the process in Gen 2 compared to Gen 1, designing the electrochemical cell itself, and also designing the electrode, the gas diffusion electrode, which was basically the key component here. And building upon this proof of concept, now we're looking at the actual implementation into a natural gas and also coal power plant. So being able to really push the process to see how effective this is, how energy intensive this process is. And here we simulated, we actually ran the experiment for 300 cycles. We tried to go with aggressive cycling for the sake of time. And we shortened the cycle to 2 minutes to be able to change the cycling process every 2 minutes. But in reality, the 300 cycles represent roughly 3 months of operation, as you see, pretty stable over time. And in terms of the energetics, we looked at different scenarios, and overall, even the most conservative scenario, still very competitive when it's implemented for natural gas or coal, flue gas, compared to the conventional processes that are out there. And in terms of where we are and where we're heading, this is probably a very general roadmap of pretty much every electrochemical system here, specifically fine-tuned towards carbon capture. We go from the building block, which is the cell, going to stack, module, unit, and also at the end, container, what we actually defined here. Right now, we are done with the R&D part of the cell, which is the heart of R&D for this process, looking at the stability test and also looking at the impact of different impurities, which brings up the TRL level for this technology to roughly 5. And now we're involved in doing the stack engineering, basically designing the stack and doing the long-term stability test, which brings up the TRL to roughly 6. We're hoping to finish this by the end of the year. And going from here, going forward, it requires less of the scientific breakthrough. It requires more of the engineering, especially on the design and packaging engineering, and something that we can easily adapt in terms of the knowledge from other electrochemical systems, such as electrolyzer and fuel cell, because of the inherent similarity between the systems. And then going from here, we basically project roughly 2.5 years of development to get to TRL 9. And we received some interest from some utility companies that are interested in terms of decarbonization of their power sector. And we always seek industrial partner, because I think going from here to here, it requires more of the industrial funding and interest rather than something like NSF and DOE. So with that, this was just a high-level presentation, and I'd be happy to talk during the panel. Thank you.
Thank you so much. Okay, so our next panel speaker is Dr. Venkatesh Silva Manikam, known as Silva. Dr. Silva, please. And I just want to remind our audience that we will have a question section right after the introductions by the panels.
Okay, good afternoon, everybody. Thank you for the opportunity to present our work at the University of Houston. So our product is actually called Ripco Thin Film Superconducting Tapes. So from the outside, it looks like a piece of copper, but it can carry, this piece of copper looking tape can carry the same amount of current as these two copper wires. In generally, these Ripco tapes can carry 300 to 600 times the current as a comparably sized copper wire. So the way this is made is through a roll-to-roll manufacturing process. Since the tape current carrying capacity of the superconductor is so high, you need only a very thin layer. It's only a few micrometer thick layer that's coated on a metal foil. So most of it is the tape is inexpensive nickel alloy and copper, and it is actually done. The tape is made by automated roll-to-roll continuous manufacturing process. So just to kind of going back in time in terms of my involvement in developing and scaling up this technology. So before coming to the University of Houston, I was CTO of a company in New York, upstate New York, for several years, where I established the world's first manufacturing operation for these Repco supernet tapes. We scaled up from just a meter length to more than a kilometer in a few years, and did the first major delivery of these Repco tapes back in 2006. And further, those tapes, we actually demonstrated the world's first power transmission cable using the superconnectors. So here kind of shows you the cutout of this cable. And this was installed in Albany between two substations. This is I-90. And that cable delivered power to about 25,000 homes. So this was a technology that was initially developed and scaled up to manufacturing. So next I'll talk about, once I moved to University of Houston in 2008, really expanded the portfolio of applications beyond power applications to high magnetic fields applications and transferring the know-how to industry. So one of the earlier work that we did was developing a process called metal organic chemical vapor deposition, or MOCVD, where we developed unique architectures and compositions to achieve superior current carrying performance in high magnetic fields. So this was developed back in 2010, and that was actually transferred to industry that licensed the technology, and it's a standard industry product for the last 15 years. So this availability of these superconductors that can carry large amounts of current, at high magnetic fields now opens up many applications, high field magnets of 10, 20 Tesla and beyond, particle accelerators, and fusion, compact fusion, which I'm going to talk about the next slide, MRI, NMR spectroscopy, and many of the applications are feasible now. So the one that's really gotten a lot of attention the last 5 years is compact fusion. So compact fusion can potentially deliver fusion energy in a much, much smaller volume than what has been developed previously. There are right now more than a dozen companies worldwide that have raised quite a bit of private funding to demonstrate fusion energy in the grid by the next decade. The thing is, the superconducting magnets that's actually is enabling technology for these fusion reactors require lots and lots of this tape. About 20,000 kilometers of this record tape just for one fusion device. and the worldwide capacity is only about a few thousand kilometers, and the tape is still somewhat expensive. So that's what we focused on in our next phase of development, is to develop advanced manufacturing technologies to fabricate high performance, low cost tapes at a high throughput. And also not only developing these technologies on a lab scale, on a bench scale, but also to demonstrate pilot scale manufacturing and manufacturing to intermediate lengths. So we have established we developed this technology called Advanced MOCVD, which addresses all the drawbacks of the commercial technologies in terms of throughput and volume and cost and performance. And so we have established pilot scale facilities at the University of Houston Tech Bridge. And so these features equipment that can include inline quality control that can monitor the quality of the tape in real time as you're fabricating it. And over the past few years, we scaled up this technology in this advanced MOCVD tool to 50-meter length, which is a nice intermediate length to demonstrate the scalability of the technology. And furthermore, what this chart shows is that in high magnetic fields, these tapes can carry 3 times the current as typical commercial tapes. So why is that important? Because in terms of today's production, the tapes are still quite expensive. It costs about $20 a meter, carries about 200 amps. So in terms of cost performance, it's about $100 per kilowatt meter, and the capacity is limited per tool. And with our approach, we expect that we can get the cost of 1/3 or $6 a meter. We already demonstrated 3 times performance and get to $10 per kilowatt meter, and that can open up a large range of applications along with the high production capacity. So to make this happen, in addition to work we're doing in the university, we also started working on a commercialization phase in the last few years. We have a small business to scale this technologies right now funded through SBIR projects, and also to demonstrate high throughput manufacturing of these advanced tapes and eventually get into full-scale production in the next couple of years. So I established a company called Amperes that is in collaboration with the University of Houston, is scaling up this technology to full-scale manufacturing, mostly funded through SBIR projects from the DOE and Navy. We have decent amount of funding right now to do this. We have a facility use agreement at the University of Houston and IP allocation agreement. And the good thing is, a lot of our students who graduate from university are now actually employees, scientists and engineers at Amperes. And we continue to scale up a world-class engineering team. So in terms of our roadmap, so like I said, we already demonstrated this 50-meter long tapes with high performance. We have current funding both at university and at Amperes to demonstrate high throughput manufacturing of these high performance tapes to longer lengths, and also in the process to deliver tapes to customers, get letter commitments. And we are in the process of raising private funds, and hopefully when that happens, we'll be able to establish a full-scale manufacturing facility and begin full-scale manufacturing by 2027. So if you're successful to do that, many applications are feasible. In terms of energy, of course, power transmission cables, especially with the data centers, we can provide a lot of power efficiently. Motors, generators, transformers, cassette compact fusion, and transportation in research. So lots of benefits feasible, and this is a technology that is really ramping up, and the demand, in fact, for this technology is so much, there's not enough supply, and so that's something that we are hoping to address with our technologies. That's it, and I'll be happy to answer any questions later on.
Thank you so much. All right, so next speaker, we can say we left the best for last. So Dr. Lian Yao, please go ahead.
Okay, can you see my screen?
Yes.
Okay, great. Thank you very much for the opportunity to speak in the panel. My name is Yan Yao. I have I've been a faculty member at the University of Houston since 2012, and my research mainly focus on material science and electrochemistry, particularly for energy storage materials such as lithium-ion batteries and beyond lithium-ion batteries. That's the name of the company we founded called Beyond, Beyond Lithium. And one of the technology we have very high interest and confidence is that sodium-ion batteries. That's I would like to share with you today. Sodium-ion battery research actually started in 1960s, actually before lithium-ion batteries, but why now is the inflection point for mass adoption of sodium-ion batteries. Last year, 2024, is the year of sodium-ion batteries because there's many Chinese companies have already moved from labs to factories, such as CATL, Hainan, and Eve Energy. There's a big lithium-ion batteries in China. There's also large-scale commercial deployment expected to more than 100 gigawatt-hour for sodium-ion battery in 2026. And also global demand for affordable, scalable storage is also accelerating, particularly with the wind and solar in combined for energy storage. And the current cost and the resources pressure of lithium-ion also makes sodium a very attractive alternatives. So on the right here shows the prediction of the global sales of sodium-ion batteries in the next 5 years. So from $1 billion, about more than $6 billion. This is about assuming a relatively conservative linear growth, but also more optimistic prediction is about exponential growth that would lead to about $30 billion. That's about 10% of the global battery production in 2030 by a company. So what's the holding back mass adoption of sodium-ion batteries in the United States? We know sodium battery have many advantages. They're abundant. Actually, US has the most sodium ash, which is sodium carbonate as raw materials. And sodium battery is also safe and durable and relatively low cost, and also perfectly fit for the lead acid replacement and great storage, as well as fast charging services. However, traditionally, the current sodium batteries have low energy densities. For the same reason, the costs are relatively high in terms of $1 per kilowatt hour. Also, currently China dominates the supply chain, and there's no domestic U.S. supply chains. So all the cathode anode electrolyte has to be synthesized or imported. So also the trade policy and tariffs is makes it further challenging for domestic sodium-ion production. So at Libyan, we propose a solution of two core technologies. One is the novel sodium-ion cathode technology. We develop higher energy density sodium-ion cathode with intrinsic safe material. Also, we have higher compaction density. So for the second technology is anode-free technologies. In this case, we eliminate conventional sodium anode material and develop new electrolyte and current collector technologies to simplify the manufacturing, also reduce the cost. So by combining these two technologies, we develop low cost and high performance sodium batteries that show very high energy density, about 180 to 200, which is even compatible, even higher than lithium iron phosphate based lithium-ion batteries, but also shows extreme temperature tolerance. This battery can work in harsh conditions, such as minus 40 degrees C or 70 degrees C, and expanding the applications for the batteries. Also, the anode-free architecture eliminate the materials import from foreign countries and enable 100% domestic sourcing, and also simplify the device fabrication. So for the cathode materials, we call the NIPP. So this is a material based on all the abundant elements, such as sodium carbonate, iron phosphate, and carbon and water. Okay, so they adopt the same facility used for the manufacturing of LFP. So last year, the global LFP manufacturing is about 2 million metric ton. So we can use the same facility for scale this material. And also we have a patent method of high compact density, 2.4. So this is actually the highest in the field for NPP in terms of which can convert to highest volumetric energy density. And we have a lot of expertise, know-how in scale of the condition, the particle size, and also dopant in this NPP synthesis. Second innovation is our electrolyte and the current collector to enable this anode-free compact anode materials. With this new electrolyte, it's a weakly solvating and fluorine-free and non-flammable electrolyte. We are able to show extremely reversible sodium plating and stripping, more than 99.9% cooling bay efficiency. Okay, and and also this material electrolyte is very non-flammable, improve the safety of the batteries. By combining together, this is the battery performance. We show at a very high rate, at a high -20 degrees C, still maintain 90% of the capacity, and the cell can cycle over 1,000 cycles at the fast 6C charging discharging condition. So putting this technology in the same landscape with other sodium-ion batteries, as well as LFP batteries, you can see our technology shows the highest volumetric and gravimetric energy density. So cost is also extremely important for the energy applications. Here we conducted techno-economic analysis in terms of the cost. The cathode NIPP itself is about $3,000 per metric ton, and translating to the anode-free device, about $17 per kilowatt hour. Right, this number is lower than that of the LP graphite, and in terms of cost of the goods for sales, it's actually reached the price parity with LP graphite systems at the scale. So this is the team of the company. We have 3 co-founders with Dr. Matthew Lee. He's a lot of experience in the IP and the commercialization. He served as a CEO and has been serial entrepreneurship and venture builders. And Dr. Leonard Liang, he's the CTO of the company. He used to be a research assistant professor at the UH, and we have been working together for the last decade. We also have Alex Shah, he's the VP of production. He's a former CTO of Austin Elements and expert in the battery recycling and LP synthesis. So also we have VP of business development for Ivan Eriksson. He's a former CEO of Tex Power. So the go-to-market strategy, we focus on 2 phases. The first phase, we are working with some defense companies and lead-acid companies to validate our materials and also test it, conduct the battery testing and validation at low temperature and cycle life and safety testing. So when we focus on the start-stop battery market for EVs, as well as for the drone market. For the military drones market, the higher the latitude they go, they require lower temperature. So that's perfect for sodium-ion battery applications. Phase 2, we're looking at grid-scale storage, where energy storage will be the bigger market, reaching more than 50 billion in 2030. And we are currently working with OEMs of car manufacturers and other grid storage companies to validate our materials. So currently we can produce kilogram materials per day, and we are in the phase to raise the funding to scale up to the 100 metric ton per year scale. So with that, I would end here, and thank you very much.